career. And I'd also like to welcome our speaker today, which is Dr. John Ortberg. John is not only a colleague, but a friend of mine. We both got our PhDs at the University of California, Santa Cruz, and now he's at the Air Force Academy in Colorado. So, John, why don't you start us off here and let us know what you're going to be talking about today?
Okay, so I apologize. My camera mount is broken. So this background is just kind of sitting by itself. I'm going to be talking about some sprite observations that we've made here with the U.S. Air Force Academy over the Texas Tech Lightning Mapping Array. So a little background. Sorry, let me put this into. Okay. Wanted to make sure that I was sharing the right screen. Um, a little bit of background into sort of what these campaigns are. At the at the U.S. Air Force Academy, there is a department called the Space Physics and Atmospheric Research Center. It's led by Jeff McHarg, and they've been doing these campaigns since about 2005. And they will drive a bunch of equipment down, and near Langmuir Labs, there's a big mountain peak, South Baldy, and they will put up cameras during some moonless nights in late spring, early summer, to try to make some sprite observations over the Great Plains to the east. And it's kind of a boom or bust campaign for the most part, which I'm sure that many of us are used to. And so there will be some years where they'll go down and they'll get, up to 100 sprites. And then some years they might see nothing, or they might be stopped in by weather at the viewing location. But overall, they've collected quite a few hundred of these over the last couple of decades, and there's been some publications on them, but there's still lots of analysis that can be done on data that's already been recorded. What they will generally bring with them is one high-speed camera and one kind of low-speed camera, where basically the high-speed camera will give you great time resolution with a much smaller spatial field of view, and then the slower 30 frame per second camera will give you a much wider field of view, but obviously less time resolution. This is a video of the high-speed camera. So they actually started off with these at about 10,000 frames per second back in 2005. Recently, about 5 years ago, they upgraded to a new camera that does about 100,000 frames per second. And so they're getting into the 10 microsecond time resolution. And that's pretty important because a lot of streamer behavior happens on a time scale of around 10 microseconds. So what you're seeing here, a bunch of streamer heads will move, and you'll see them start to split, branch, die out, collide. And a lot of those activities will happen in the 10 microsecond time scale. And so up until 5 years ago, they would generally be able to see, for example, when a streamer head would branch. But now you can actually see what goes on during the process. So the brightening of the streamer head and so on. It also just looked really cool. The 30 frame per second camera, you can see, so this is basically 2 hours of footage, and it's showing all of the sprites that happened during that time. And we're basically looking at some storms over Texas. And it gives you, it's about 20, I think, degrees of azimuth. So for reference, if you are about, these storms are about 400 kilometers away. So 20 degrees of azimuth in the field of view will give you, roughly 2 degrees of latitude in this case, since we're facing east, that the camera will be able to see. So we're able to capture about maybe 60 to 70% of the whole spatial extent of this thunderstorm with this field of view. Obviously, you can make trade-offs by widening the camera angle, but then you get less spatial resolution on the sprites. And you can see some of the sprites kind of happen off the screen to the right, and so we might miss them entirely. You'll also notice there's a pretty big variety, different types of sprites, called basically their morphology. So essentially, whether or not they are uh, tall or wide or long lasting, short lasting, how bright they are. Um, there's not necessarily a lot known about what causes the different morphologies of sprites, but we're certainly collecting a lot of them and hoping to at least start to answer that question. You also notice some of them will connect all the way down to the cloud tops, and I don't necessarily know the answer if uh, that would turn it from being classified as a sprite into a blue jet. You can make out a little bit of the horizon here in this image, and a little bit of the lights of the town down below, just to give you some perspective on what you're seeing. So the specific storm that we're looking at the moment is from June 3rd, 2019. And uh, the nice thing about this storm is that the sprites all seem to occur right over the West Texas LMA. And the range of the LMA is shown down on the bottom left. Those red dots in the center of the plot are all the Texas Tech LMA. Um, and then the shaded regions around it represent where there's good 3D mapping resolution. And then the wider circle is good 2D resolution. And then the dots up in the upper right are the Oklahoma lightning mapping array, which a lot of the sprites on the June 2nd storm occurred over. We've not done analysis on that yet. It's obviously a bit farther, so we don't have as good of optical resolution. The June 3rd storm, we initially identified about 20 sprites with their parent flashes directly over the LMA. So the wide field of view camera that I was talking about has about 2 hours of footage. And so if you do the math on that, if you have a 30 frame per second camera, you end up getting about 200,000 frames. And that becomes very difficult to sift through. And originally, the way that they would look for sprites is just watching the video and sort of looking by hand to see if there was a sprite, and then they would write down the time of the sprite. Some of them were seen in real time, and so when they were at the observation site, they would just jot down the time that they saw the sprite. Um, but there was a lot of potential to maybe find more sprites in that footage for a couple of reasons. First of all, it's kind of hard to just sit and watch for 2 hours and make sure that you catch everything. Second of all, some of the sprites are so faint and brief that it's actually really hard to tell in real time while you're watching the video that a sprite even occurred. And so there needs to be a way to identify a sprite versus just the noise that you would see of a 2 hours on a camera. Um, so what we did for this was we used essentially the same algorithm that's used with LMA data to classify um, LMA radio sources into individual flashes. Um, and they use a clustering algorithm called dbScan. And you can kind of see the difference between a standard clustering algorithm called k-means versus dbScan at the bottom. Most clustering algorithms are good at being generalized to higher dimensions. So obviously not just 2 dimensions, but then you can work up to 3, 4, 5, however many you have. The problem is they tend to mostly just work by absolute distance. So in other words, if there are 2 points that are close to each other within those 3 or 4 dimensions that you have, they will be identified as the same cluster, even if it looks like they should belong to 2 different structures. As you can see in the data on the bottom, this is a very clear example of where you have 2 separate structures, and you would want a clustering algorithm that can pick them apart. And so that's what LMA flashes use. The standard clustering algorithm is called dbScan, and it basically works by finding an area of high density, and within that high density area, it will continue to expand whatever structure it is defining until it starts to run out of these bordering points that you can see on the bottom right. Um, Now these bordering points, there's a lot of parameters you can leave open in the algorithm. And when we took the algorithm originally, it was obviously optimized for uh, finding lightning flashes in LMA data. And so what we had to do is we had to modify it to work for sprites in our camera data. Um, and there are lots of very straightforward cases um, where you can immediately identify the sprites, but then there's a lot of edge cases and a lot of false positives. So to give kind of a brief overview of how we did that, um, we I mentioned before that there were 25 sprites that we saw by hand before this process, and then when we started using this process, we found an additional 55 sprites, but that ended up amounting to 553 total frames. Now, uh, when I say 70 total sprites, it's actually interesting that when you watch the footage of these sprites, it can be hard to distinguish whether or not certain frames are the same sprite, or a new sprite. And so all that we did was we said if there's ever a blank frame from the camera in between two frames of sprites, we'll call that a new event. But there's plenty of events that seem to last a second where there's probably different sprites that are popping up and they just happen to overlap each other in brightness. You can see the output of the algorithm on the bottom right. And all that it does is it just takes the original camera image and it converts each pixel into a numeric brightness. If that brightness is above sort of the background threshold for the camera, then it's considered to be a bright pixel. And then we run that clustering algorithm on just those bright pixels, ignoring all the dark pixels. And when we find something that is sort of sprite shaped, we will pick out that frame as a sprite. Now, what do we mean by sprite shaped? Um, Basically, anytime that we found 70 bright pixels per cluster, so in other words, it has to be big enough. It also has to get high enough above the origin. And the reason for that is since we're recording a thunderstorm, you're going to see a lot of flashes that are down at the bottom of the camera. And so when we originally tried to just pick out bright pixels, of course, you end up getting a bunch of frames that are just normal lightning, which is not what we're interested in. Um, we also had to remove stars. Stars are obviously going to be very bright clusters in the camera's field of view. And depending on how bright they are at certain times, as they move through the camera's field of view, they might get misidentified for a sprite. So we would essentially have to remove anything that was circular and small. And then we still ended up with a number of false positives anyway. I think this is the camera. Okay, so this shows all of the sprites that were identified just by the algorithm itself. I got to use these play controls. And you'll notice some frames that we had to actually end up manually removing, like this one. There's kind of no way to systematically or automatically determine that this thing is not a sprite because it sort of looks like it. It's a bunch of bright pixels together. It turns out we think this is a bug and it happened twice. So I don't know if we're ever going to be able to come up with automatic bug filtering, but it certainly was setting up some false positives. When you get just 25% of them being false positives, it's pretty simple to remove them manually. It takes less than an hour. The problem is if you don't have this algorithm in place and you just take bright pixels or bright frames, then you end up mostly just watching standard lightning lighting up the frame. We've actually sent this algorithm we're collaborating with a group down at the Auger Observatory that's looking for sprites in Argentina. And they've actually adapted the same algorithm for their own sprite search, and it's been pretty successful. So it's essentially a way of turning a non-event based camera into an event based camera, so long as you have the storage for it. What this has really allowed us to do is sort of pick out the time and places that the sprites are happening relative to the LMA. So this plot, as well as a lot of plots that put a bunch of different data sources together, will probably take some explaining. I'll try to do my best here, and I tried to keep this as simple as possible, but it's as with everything that we're working with here, it's a lot of different data sources. So all the red dots are, they should look very small, and those are just LMA sources. In other words, those are places where the lightning mapping array said we saw some sort of flash. Most of those that it will see will be intracloud flashes. Um, the blue dots, on the other hand, are places where our camera picked up pixels that it said were sprites. And this is all plotted where the x-axis is the azimuthal angle from our camera. We obviously don't know the exact location of these sprites. We're just seeing a two-dimensional projection because we're looking at our camera. And so we have to just map things out in terms of azimuthal angle. So that means we also converted the lightning mapping array data, which is in lat long, into azimuthal angle from our observation point. The black lines, on the other hand, represent the edges of the camera's field of view. And so you can see that there were, I think, 7 times that we moved the camera slightly. And now it's just to try to keep, where most of the spread activity was happening, to sort of try to keep that in frame. Now the pattern here is very stark. And so obviously there's some areas of the storm that we weren't looking over. So we can't say with any certainty that there were no sprites happening in that area. But we can definitely say with where we had our camera's field of view that most of the sprites tended to happen far to the left of where most of the lightning activity was happening. Now, we were mostly looking due east. So when I say that most of it happened to the left, that's kind of synonymous with saying happened to the north. It's just I'm trying to be precise about the perspective that we had from our camera. There's a big gap you can kind of see in the time, which is on the y-axis. And that gap is just when we did not have the camera recording. The I know it's unusual to have the time on the y-axis. The reason that we do this in some of our plots is because we try to keep the x-axis aligned with the x-axis of the camera itself. So in other words, you can sort of match up the bottom of the frame with the bottom of this graph. So you can see if it looks like the sprites are happening to the left in the picture frame, they'll also be happening to the left in this plot. This is a still radar image of the storm itself. I think kind of early on, so this would correspond to 4:30 in UTC time. And you can see this, for some reason my mouse is not going over the presentation. Oop, didn't mean to click that. Yeah, for some reason my mouse is not going over the presentation, but I can still describe it. So you can see the really dark convective cell area. Those are the dark red and orange areas. And that's where most of the flash activity in the storm happens. That's where most of the updraft is happening. Most of the charging is happening. And then kind of up and a little bit mostly north and a little bit to the west, you can see what would be called the stratiform region. And that's where there's a lot of kind of steady precipitation. And there's no active convective charging there from what we know. But from what we understand and what we've heard from some meteorologists is that as the storm is charging through the convective cell in red, some of those charges will reach the top, overshoot the cloud, and sort of drift or advect in the wind towards that stratiform region. And that stratiform region is where we're seeing most of the sprites occur. So again, going back to the previous plot, the red LMA data that we're seeing here is in the convective region, and most of the sprites in blue are happening further to the north and a bit to the west over the stratiform region. So some of the data sources we're looking at here, in this case, we have a WATOT camera that's operating at 30 frames per second. We have the lightning mapping array data from Texas Tech. We have Earth Networks lightning network, and then we have National Lightning Detection Network. As you can see, some of that data is incomplete. But with so many data sources, we end up with this problem of it being difficult to know exactly what to display. So this plot at the moment should look confusing. I have shown this to multiple people, and they have all told me that it's confusing. That is kind of an inescapable fact of all the different things that we are trying to plot. Um, I am going to go through and basically kind of do a breakdown of what all these different plots mean, and why they're important to us. And then I'll also show a couple more individual plots that should hopefully make a little bit more sense out of what's happening. Um, okay, so this is a diagram that I actually made for some collaborators who are looking to help them try to understand. Now, this also has a lot of information on it, so I don't expect this to immediately be helpful, but this is a sort of a breakdown of everything that you're seeing on that previous plot. What I would mostly call attention to in this first plot, if we focus initially on the top left plot, you'll see a pretty standard progression from red to blue that represents the time of the LMA sources. So you can see that this large discharge started at about 4:12 and 36 seconds, and the top of the plot is about a second and a half, maybe 2 seconds later. And those colors, which go from red to blue, it's kind of a standard LMA plotting system where uh, you'll sort of redundantly plot the time of the LMA sources, which are also plotted on the y-axis. But that will help you to see what that color corresponds to in a different graph. So if you look at the bottom left graph, for example, all of those dots have color that's representing time, which can be identified in the top left graph. Now, those funky looking orange squares, those are where we saw pixels with sprites in them. And again, this is all plotted on azimuth on the x-axis and time on the y-axis. So you can start to see this pattern where the sprite starts relative to our point of view somewhat to the right at about 97 degrees azimuth. And then that discharge, which is happening in the clouds, will generally start to curve to the north, or from our perspective, to the left. You'll then see a vertical line with an X. That's the timing and position of the cloud to ground strike that induces the sprite. And then all of the orange squares we're seeing are the evolution of the sprite after the cloud to ground strike. The orange lines on the bottom left and bottom right plot basically represent the extent of the sprite from our field of view. So you can imagine that those are just kind of an observer looking from west to east, and that's the width of the sprite itself. Again, because it's a two-dimensional image, we can't identify exactly where the sprite occurred, but we can identify at least what angle it was relative to us. So, for example, if the sprite happened kind of right around where the cloud to ground flash happened on that black X on the bottom left, then that means that the sprite would have spanned from about 33.5 degrees latitude up to about 34.1. The plot on the bottom right shows the charge structure of the thunderstorm according to the LMA. And it's basically just 10 minutes of preceding flashes and where it can be identified that there was a positive charge center or a negative charge center, that's shown in the plot. And again, we're seeing that the sprite is kind of centered pretty far to the left or to the north of that charge structure. The common patterns that we're seeing here, first of all, as I was mentioning, with the majority of these events, we're seeing a large horizontal discharge that's happening through the clouds and is moving to the left or to the north, and it precedes the parent cloud to ground strike by about a second. The cloud to ground strike itself will precede the sprite by about 1 to a few hundred milliseconds. And it tends to be to the left or to the north of the origin of that large discharge. And then the center of the sprite itself usually is also further to the north again than the original cloud to ground. So what that looks like is um, if we're to sort of draw a thunderstorm that has this vertical wind shear to the left, all of the main flashes in the thunderstorm are on the far right side of this image. When we see a sprite, most often what we see is the discharge will start somewhere in the center or to the left of the sprite itself, and then it will move very far to the north towards that stratiform region. Somewhere over there, we will get the parent CG for the sprite, and then the sprite itself will happen further to the left. And so it kind of all makes this arrow that's pointing in one direction. This is another way of looking at more or less that same data. And what we're seeing here is the same thing that we were seeing in this top left plot, except now we've zoomed out on the time window. So instead of seeing 2 seconds at a time, we're seeing 20 seconds at a time. And we're looking top down on the storm. So we now have latitude instead of azimuth on the x-axis. These are all LMA sources, and so we're seeing a lot of flashes throughout the middle of the storm, and then every once in a while we'll see a flash that goes far to the north, again from our perspective to the left. And if that flash, which is large and goes off to the north into the stratiform region, if it has a strong cloud to ground towards the end of it, then we will usually see a sprite. And so the sprites here are represented by those horizontal black lines, and the number of the sprite event is also shown there. So in this case, we're seeing events 16, 17, 19, and 20. So at the moment, we're kind of formulating rules to help us try to predict when we're going to see a sprite or not. And so far, the rules, generally speaking, the preceding discharge that I was talking about that goes through the clouds, it has to be large, about 40 kilometers or larger. It has to extend into the stratiform region. For the most part, that can be pretty clearly seen by sort of the center of the graph on the x-axis, about 33.5 degrees north. But obviously, the storm is moving. It's mostly moving west to east, but it's also moving a bit south to north. And so the stratiform region will change a little bit throughout the evolution of the storm. Third rule is that the preceding discharge has to eventually be followed by a strong cloud to ground strike. And then the final rule is that the cloud to ground strike has to occur in the stratiform region. Cloud to ground strikes here are shown by those the white circles with the red outline. And the size of the circle represents the strength of the flash. So you can see that all of these sprites here have some strong CG flashes associated with them. So here we can see some examples where some but not all of the rules are met. In this case, you can see the purple flashes extend quite far into the stratiform region, but they're not followed by a strong CG. We do see a CG there, but it's quite small. There needs to be a CG that is strong enough to induce a sprite after the preceding discharge. Here we see another example where again we have a large flash towards the top, but the cloud to ground strike is both not in the stratiform region, and it seems to happen a little bit too early in the discharge. Here we have an example with some large cloud to ground flashes, but the discharge that goes into the stratiform region is not large enough. So this would be about 30 kilometers or so instead of the kind of 40 kilometer minimum that we've set. And I'm referring to the green flash that you see around the middle of the time frame. Here we're seeing another example in the orange on the bottom. We have a large preceding discharge, but there's no follow-up CG flash to induce the sprite. So we're noticing this pattern, and that immediately causes us to question if there's any basis for this. So the image we're seeing on the right here is from Steve Kummer, paper in 2004, and he's drawing the center cluster with a dotted line around it, and all the small black dots is sort of the main region of the storm. And here he is plotting the charge moment change. Now, charge moment change is, I think it's like probably impulse charge moment change to be precise. Charge moment change is basically just the total amount of charge that's moved and then how far it's moved. The reference here to impulse charge moment change, it's technically you should be integrating that over time. I think charge moment change by itself will be in units of per second or per millisecond. And so here, really, we want to integrate over the whole course of CG stroke. So in the middle of the convective cell, we're seeing these small charge moment changes of 50 Coulomb kilometers or less. And then out in the stratiform region or just outside of the main charge center is where we're seeing the largest impulse charge moment changes. So this matches up pretty well to what we're seeing. And I'm going to go back a few slides for this just so we can see an overview of the storm. So again, this is the top down. Oh, sorry, I missed it. This is the top down view of our storm. And the red dots represent all the flashes in the storm and the blue dots represent the sprites. So if we're to believe that CG's cloud ground strokes with large charge moment changes are inducing our sprites, this matches up pretty well with the paper from 2004, where we're seeing a lot of kind of normal discharge activity over the main convective region of the storm. And then to the left or to the north, we're seeing what are probably some of the higher charge moment change flashes, and those are inducing the sprites in that region. Okay, making sure I get back to where I was. There we go. The two main kind of follow-up questions that we're tackling at this point is, first of all, why might the impulse charge moment change be larger when we see these conditions? So why is it that when we have a preceding discharge that is large, that goes into the stratiform region, and then is followed by a strong cloud to ground flash, why is it that the charge moment change then would be larger? I think we can definitely think of quite a few reasons for it, but it is not necessarily straightforward to come up with a comprehensive picture that totally matches what we're seeing in the data to then be able to say, this is what the electric field should look like up at the altitude of these sprites. The other thing that we're seeing is this so-called lateral offset. And this lateral offset has been seen in sprites for a long time, where basically you'll have the cloud to ground flash, and then the sprite is often not centered directly over that cloud to ground flash. Sometimes it can be seen 10, 20, up to close to 100 kilometers away from the cloud to ground flash. And so we need to be able to come up with some sort of picture as to why that happens. Now, generally speaking, if you were to look at this picture of a thunderstorm, this one, yep, this one. If you were to imagine that you had, and again, I wish my mouse was working for this. I'm like clicking, but it's just making it click. Okay, that's fine. If you were to imagine that all of those positive charges on the top of the cloud were all of a sudden carried to the ground, then you would get a big charge moment change that would induce an electric field change in the upper atmosphere. In other words, you're kind of exposing the main negative charge center to the upper atmosphere, whereas before it was shielded by that upper positive. So if you all of a sudden expose the main negative to the upper atmosphere, then you're going to induce a strong electric field pointing down towards that negative charge center. And if that new electric field crosses the streamer threshold, that's generally when it's thought that you're going to get sprites. So we need to basically make sure that our picture accounts for not just an electric field that's strong enough to create the streamers and the sprites, but we need to make sure that the electric field hits that strength threshold uh, further to the north of the storm than the cloud to ground flash itself. There has been some work on this before. So what we're seeing here is a paper from just a year ago by a couple of folks out of Tel Aviv University. And this is just a modeling paper, so this is not based on any data, but they're essentially what they did is they created a thunderstorm with lots of vertical wind shear in their model so that the charge structure itself was highly tilted. And then they removed the positive charge from the top to try to induce an electric field change in the upper atmosphere. And what you're noticing here is that the greater the tilt of the storm due to that vertical wind shear, the greater the tilt of the charge structure, then you would actually get more of an offset of the electric field change um, to the right of the storm. Now, in their case, they had the storm tilted to the right. From our perspective, we were looking at a storm that appeared to be tilted to the left, but obviously the physics behind it are the same. And so their modeling shows that the strongest electric field change, which are shown by those contours, and the green is the strongest tilt, the black is the weakest tilt. That basically the stronger the tilt of the storm, the stronger the vertical wind shear, then the further the sprite is going to be offset from the cloud to ground flash. So with that theory, we're kind of now working on some new visualization methods. The plot on the left, pretty similar to what we were seeing before. So you can see the LMA data is just kind of the normal points. You can see the sprite pixels as those orange boxes. And then we've added the Earth Networks cloud to ground flashes, which you can see in the red boxes, and the NLDN flashes, which you can see in blue. The numbers there correspond to the strength of the current, the peak current in kiloamps. Now, just knowing the current doesn't necessarily tell you the charge moment change. Unfortunately, neither network publishes the charge moment change or tries to calculate it from the data. So we are working just now with the peak current. And so you can see that it's a strong peak current that triggers the sprite, and that again, the sprite in those orange pixels is further to the north than the cloud to ground that triggered it. On the right-hand side, you can see more of a traditional lighting mapping array type of plot. And so here you'll have six plots that are kind of all showing different variables on the X and the Y axis. And the orange dots or the orange shaded regions are showing where the sprite occurred. And because we don't have triangulation on all of the sprites, now, fortunately, we do have triangulation from a second camera source on a few of the sprites, but most of them we don't. So here we're just sort of estimating the distance to be about 400 kilometers away from our camera. So if you take that, the sprite occurred about 400 kilometers away from the camera, which is where most of them tended to occur that we know of, then you can see where the sprites line up with the traditional LMA data. Now, I'm someone who just started looking at LMA data within the last couple of years, or really within the last year, maybe a couple of months is a better term. And this still looks super confusing to me. I think to some of them, this makes perfect sense if you're an LMA scientist. It's a lot of information, and it can be very tough just to follow along with the flash. Obviously, you're plotting something that's four-dimensional, and you're trying to do it in a bunch of different two-dimensional panels. We can look at the top left plot here, A, and you can see a number of kind of vertically spaced discharges, and then you see the sprite occur at what is probably a cloud to ground flash that's happening with some of those green dots. Unfortunately, LMAs don't see cloud to ground flashes very well. They tend to see only short, sharp accelerations in electrons, which are really common in streamers, streamer zones, negative leaders, but you're not going to really see a return stroke, which is much more of a large scale current. Um, on plot B, you can see the sprite as those orange pixels and where it would be relative to um, the flash itself from a top-down view. Again, this is assuming that the sprite is occurring at about 400 kilometers away. That's just an estimation. The time plot goes from dark blue is the earliest time to bright yellow is latest. So you can see that the flash actually starts on the far right of our plot to the east and then kind of evolves up to the north and then starts to spread around to the southwest at the same time. Um, so these are different ways that we're trying to visualize the data. Whether or not this is going to help solve any problem is not immediately answerable. There's a lot of we have 3 to 4 different data sources. Try to plot it in ways where we can make sense of it and make sense of how they correspond to each other. And then once we can kind of make sense of it, then we'll be able to know whether or not it was worth it to put it in that form. Okay, so what's coming up next? We're hoping to improve the NLDN data set that we have. We're going to get a more comprehensive one, hopefully in the near future. As I mentioned before, there's a lot of previous storms that we have not even touched yet with this analysis. So we can see whether or not this pattern of sprites occurring away from the convective cell in the stratiform region is something that occurs across storms or whether it's unique to particular storms. We're going to want to do some very simple electrostatic modeling to be able to see if our conception of what the charge structure of the storm looks like and what the CGs does to the charge structure, whether or not that matches up with where we're observing the sprites. Steve Kummer is also the one that sort of maintains the charge moment change data, so we will not be ashamed of going to him as many times as it takes to try and get a response. Okay. I think that's just the video playing. So that's the end of my presentation. I've kind of laid out the slides here just in case there's any questions if you want to refer back to a specific slide. But other than that, thank you guys for your time.
Thanks, John. That was really interesting and really great work. And we now can open it up to any questions anybody might have for John. You can type in the chat or just turn your mic on and ask.
Hi, John. This is Jeff McCarr. Great presentation. Say, I was wondering, we've been talking, you and I have, about what electrostatic modeling might make sense. And I was wondering if you might share with the audience some of your thoughts on what we might do for sort of a simple-minded model to get started on this lateral charge or this lateral offset of where we see the sprites and the LNA sources. Thanks.
Yeah, so I think probably we can look at that best in slide number 16. Yeah, it was this one. So, I think with all thunderstorm modeling, you have to try to keep things as simple as possible, which means they're going to be, to some extent, unrealistic. I think that the simplest approach here would be to take either a common dipole or tripole model of a storm. And you can kind of see with this one that's a little bit tilted, you can almost imagine parallel capacitor plates, but one is offset to the side. And so some electrostatic modeling we could do is to basically take 2 parallel capacitor plates and then either displace the one on top to the left or rotate the entire contraption just slightly to 5 degrees or so. And then to model what the cloud to ground stroke does, you would essentially chop off some of the left turn edge of that positive capacitor plate. And then you could model what changes in the electric field and whether or not that change is strong enough to induce the streamer threshold and then where that happens. So in other words, with this tilted storm structure, if you tilt it more or rotate it and then chop off the positives on the top left, does that induce the strongest electric field further to the left of where you chopped it off or directly above where you chopped it off? If the answer ends up being further to the left of where you chopped it off, then that would match up with the lateral offset that we're seeing. If it goes directly above where you chopped it off, then it does not match your observations, and we're kind of back to the drawing board for different ideas.
So, any other questions? Well, if there's no other questions, I just want to make a big thank you to John. Really interesting talk and interesting work. So really appreciate you giving that to us today.
No problem. Thank you yourself, Jeff.
No
Both
worries.
Jeffs.
All right.
All right.
Yes, well, a link will come out maybe in the next week or so that you can see and people can. We'll email it out to the whole group, the whole ASE group, and people will be able to look at it on YouTube. So.
Perfect.
All right. Thanks, everybody.
All right. Appreciate it. Take care.